technologies. As the outcome of the technologies, mobile games have become one of the most daily recreations for people when they are off work. Gradually, the mobile game industry is worth billions of dollars, with companies spending vast amounts of money on the development and marketing of these games. As for mobile game advocates, we will in this project combine this mobile strategy game dataset with knowledge we learn in class to classify the dataset using some of the classification algorithms.
Now let me introduce the data source. In order to tackle our topic, we certainly need some enormous and trustful data set to analyze. And we found this particular data set from Kaggle, which contains about 17,000 strategy games on the Apple App Store. It was collected on August 3rd, 2019, which is using the Apple Store iTunes API and the Apple App Store sitemap. And the CSV file contained from the link showed above collected the game's size, developers, user ratings, drawings, and descriptions of all each games. And in order to do the classification of the games, we firstly come up with the K-means clustering. Well, K-means clustering is one of the classic unsupervised learning, which is used when you have the data without the defined categories. And the data points are clustered based on the feature similarity, which in this case, you are going to select several features in the database and run the k-means and come across to compare the clustering results. And before to begin the k-means actually running, I actually look up to one of the papers showed from New York University, which also used the k-means to do the clustering and to do the classification for the video game playing. It took the game features as one of the standard, but in our dataset, in order to acquire the feature with the digitalized version, we transformed the drawing, which was originally a set of strings of names and any descriptions, and we changed that into values, which could be calculated and for different games, which are more easily for us to do the analyzation. We certainly include more various conditions to consider rather than just two features in the study. And like the release year, age ratings, and user count ratings are also into the comparison. And before that, it is very important to reiterate that a drawback of k-means is actually we do not know what's going to be the number of the clusters. And before to know what's going to be the optimal k is, we could use the album method, and the implementation of the album method are showed from the left screen, and we're going to calculate the distortion, and the optimal value is actually reached at k equals to 3. You could see from the right screen through the graph, and the k equals to 3 is indeed a good choice for the dataset. And here are the actual implementation of the k-means, which you could see from the code that n clusters are equal to 3, which are we going to separate the data to 3 clusters. And since we cannot take all the features into considerations, so we do the PCA first, and we could extract 3 principal components, which is going to be created for a three-dimensional graph. So we're going to create, so we do the data cleaning of the dataset, so which is you now see the principal DF, which is going to contain the 3 columns of the principal components. And after running the k-means, we need to do the visualizations. All the code start with the AX are the actually to do the visualization of the graph. And the results of that one is showed in this slide. And you could see the PC1 and the PC2 and the PC3 to be the 3 axes. And from the graph, there are the scatter plot showed in the 3 different colors, which are the 3 different clusters, the blue, purple, yellow. And now that's the k-means.
Hello, my name is Jin. I'll be introducing the principal components analysis that we did in our project. The purpose of principal component analysis is to first reduce the dimension of our data, because some of our logarithm, as mentioned above, need a lot of computational powers. In order to speed up, we reduce the dimension to make it less computation. Second, we use PCA to visualize our result from high-dimensional into a 3D graph. Lastly, we will see a comparison of running PCA to reduce the dimension before each classifier and just running the classifier and visualize it by PCA afterwards. Alright, our original data has 11 features and we selected one that we interested in, and also we converted some categorical data into numerical. And after data cleaning, we end up with 6 dimensions, and then we use PCA to further reduce it down to 3 features. And here's the result in the 2D graph. The one on the left would be PC1 versus PC2, and the one on the right would be PC1 versus PC3. It seems like random points, but if we visualize in 3D graph, it is much clearer. So right here will be our 3D graph. As we can see that it looks like there's like 4 bars on each corner and some points in the middle between the bars. Okay. And now we see the comparison between running PCA before and after k-means. We only did the comparison with k-means because the other two classifiers need much more computational power and takes a really long time without dimensional reduction. And as we can see, run PCA after k-means will give us a better result. We can see the points are clustered well, in contrast to run PCA before k-means, which the cluster gave the data points like mixed together or classified horizontally with labels 1 on the bottom, labels 2 in the middle, and label 3 on the top, as we can see. So based on the result that show, it seems like PCA should be run afterwards if it's possible. Thank you.
So here are the steps for spectral clustering. The first step is using the PCA reduced data and using the spectral clustering function from sklearn package to conduct spectral clustering. The code is given below. The variable, in this case full label SC, contains our labeled data and provide us with cluster each number belongs to. And the second step for a spectral clustering algorithm is data visualization. We have used the plot method in Python, and we draw a scatter plot for our spectral cluster data. As you can see, the code is given above, and the result is shown on the right. So we have in total of 3 cluster centroid, and each of them has been marked by different colors. So here are some descriptions and discussions for spectral clustering. So based on the steps in previous slides, I discovered that the data have been grouped by our spectral clustering algorithm. Therefore, our experiment is set to be successful, as you can see it on the right. However, since the third cluster has only a few data, which is the green cluster centered in this case, the part that does not go well is that I should have written a function to optimize the number of clusters we should use. So instead of 3 in this case, we should have used 2. The thing that I did not expect is the huge time complexity of the spectral clustering algorithm, which is n to the 3. So we have total of 7,561 data. It took me almost 1 day to run the algorithm itself. I learned how to implement spectral clustering algorithm to real-world example during this project. And the thing that I could improve is that I should write another function to optimize the number of clustering centroids, as I said. And also, if I ignore the huge time complexity, which is if I have time, I would definitely also cluster an on-PCA data and run PCA after to make comparison with the on-PCA result. That's it.
Hello, my name is Zimu Lee, and I'm here to introduce you the second approach we use for our game recommendation system, the mean shift clustering method. According to Chen's 1995 literature about mean shift clustering, it's basically another kind of k-means clustering, but we don't have to define the number of cluster beforehand. Instead, we set a number of random cluster centers and set a radius to each centers and use recalculation to mean method similar to k-means to find out how many center converge in the end and therefore have obtained the final cluster for the data set. The idea is that we set a radius to each initial cluster center. This radius is called the bandwidth. Then we recalculate the mean of each cluster center given their bandwidth. After number of iterations, some of the initial cluster center will converge, and that's when we say stop, because that's when we have all the cluster completed and we can see the result. So this is a figurative illustration of the mean shift clustering. As we can see here, there's a 4 random initial cluster center we give to this data set. And now we see, for example, this cluster has 2 data points within, so we calculate the means of these 2 data points and move the cluster. And eventually, these 2 clusters on the left side will converge to this one, and these 2 clusters on the right side will separate to these ones and give us the correct clusters. And now we'll implement this mean shift cluster method on our data set. First, we're going to use the data set that's already has this dimension reduced to 3 dimensions provided by our PCA procedure above. And then we'll use the sklearn built-in function to estimate the optimal bandwidth. Here we see the optimal bandwidth for the PCA dataset is 10.05. And then we'll use the sklearn package provided tools to conduct mean shift. And after we conduct mean shift clustering on our dataset, we find out that there are 4 clusters. Then we'll visualize it. As you can see, this 3D graph is the visualized version of our cluster. There's 4 distinct clusters. After manual inspection of each clusters, we found out that the game is clustered not so much based on their genre, but based on its user rating count and price. We believe that this could be caused by our way to conduct PCA before the cluster, but generally the final cluster does make sense. For example, Sudoku and Sudoku Free has higher user rating counts and is clustered in a different cluster than the game Expert Sudoku. And these, even though these 3 games has identical name and identical genre, but based on its user rating count and price, the algorithm was successfully clustered them into different cluster and which benefit to our recommendation system. And to improve this clustering method, its implementation on our data set, we believe that we can potentially adjust the bandwidth and see if it gives us more clusters or it gives us less clusters.
So here are our 3 results for 3 different classification algorithms. As we can see, the k-means algorithm's result is shown on the left, and the spectral clustering in the middle, and the mean shift algorithm is on the right. So here are our discussions and some conclusions about it. So based on our visualization results, we can see that spectral clustering algorithm is not suitable for classifying our data. Instead, k-mean algorithm performs really well, and we can see from the k-mean result that our data have been partitioned and grouped by k equals to 3. Moreover, because we conducted mean shift clustering algorithm and the algorithm itself determines k equals to 4, we cannot directly compare this model with the rest of 2. But based on the classification result, we can pretty much tell that mean shift clustering algorithm performs equally well with k-mean algorithm. Overall, k-mean and mean shift algorithms best suit our data, while spectral clustering not in this case.